All right, it is 4 o'clock on a beautiful Monday afternoon. My name is Bob Amar. I am an independent school math teacher in Atlanta, Georgia. And this is, I guess, the second in a series of videos where we're going over some of the free response questions from recent years in statistics. So I'm going to go ahead and get started on that. This is a fairly long set of questions. All of the questions are in play this year, and so I think it's important that we go ahead and try to get each of the questions their particular due. If you have a question about anything that I'm talking about, let me present my solution first, and then just pop a question in the Ask a Question button. Come into play today a little bit as well. Make sure you give us a follow, subscribe on YouTube at Think Fiveable. So it's important that we'd love for you to keep in touch with us as we continue to put out this content for you, and let us know what you think. Let us know if there's something you in particular want to see. Okay, so again, we're going to just jump right into the 2018 solutions. Again, all 6 questions are basically in play this year. So we'll just go through the whole thing. This stream may actually run over 60 minutes. So, I hope you will indulge me in that, but there's a lot of good material in this, and I want to get that all out there for you. So if we need to, we'll refer to this slide, but this slide will be in the resources at the end, where it's just, here are some things to think about. AP Stat is not real famous for giving you like very clear guidelines as far as what in particular is, they'll tell you to do something in context, but then they won't actually say, hey, make sure you do that in context. Oops, that's too far. It's one slide too many. Okay, so let's go ahead and let's jump right in. Okay, it will help if you pull up the questions alongside, because I'm not going to really be able to do a great job of showing you all the questions at once. I just don't think that's going to be a real good use of screen space. So let's go ahead and you make sure you pull those up. They're available on the College Board website. If you are following along, when you're doing the replay, you can pause this video at any time and take a look at what we're doing. So here's question 1. The manager of a grocery store selected a random sample of 11 customers. Sounds exciting. And they actually plotted how long it took them to check out against the number of customers in line at that time. Okay, and then they collected that data. They threw that all, it looks like, into Minitab is the format here that you're seeing, and they came up with these numbers. And you'll notice that there is no mention at all of a line other than the computer output. You're supposed to be able to reconstruct this computer output from the given information. So let's go ahead and make sure that we can do that. So part A, identify and interpret in context the estimate of the intercept for the least squares regression line. Okay, so I'm actually going to go ahead and write the whole line. And remember that what you're looking for is this stuff right here, this thing that says coef. These tell you the values of things. This thing that says constant, this is the y-intercept. And then customers in line is the explanatory variable. Okay, you are required to know that what you're trying to do is predict the response, and the response is plotted on the vertical axis. So the response is the time to check out. Okay, so identifying and interpreting in context the intercept. That's going to be this guy right here. So this is part A. Okay, and so you don't need to write the equation of the line. You just need to know that for part A, the intercept for the least squares regression line is 72.95. Okay, and it says interpret in context. And what that says is the y-intercept, is when the horizontal variable, the variable on the horizontal axis is equal to 0. So what we're looking at here is when there are no customers in line, ahead of the person when there are no customers in line other than the person checking out, I guess. We can now we have to use a set of language that indicates that we know that this is a model. Okay, so it is not guaranteed that a person in line will take 72.95 seconds at this very moment, but we expect, or on average, or we estimate, the checkout process takes 72.95 seconds. Okay, or you could say the let's go ahead and add on average here. I think that's safest. Or we predict that the checkout process would take 72.95 seconds. Just as long as you don't just write the checkout process takes 72.95 seconds, because you don't know that it does, right? Okay. Part B, identify and interpret in context the coefficient of determination R squared. Okay, so now here is everyone's favorite part. There are two things that say R squared, right? Don't use R squared adjusted in AP. Okay, it has a use in more advanced statistical methods. This is not the time to use it. This is the one that you want. Okay, so this is our R squared value in part B. Some of your teachers might have given you a boilerplate or a Mad Libs for this. Okay, so for part B, R squared is, you can write 0.7333 if you want. You can write 73.33% if you like. Either is fine. Just make sure if you write 73.33, that's not good. Okay, you need the percentage sign there. Okay, and so the boilerplate that I like to use is 73.33% of the variability in response variable. Okay, so the response variable goes here. In this case, checkout times. Maybe I should put this in a different color. Blue. Okay. All right. 73.33% of the variability in checkout times can be explained by the linear relationship with, and here's the other part where you insert something. This time you insert the explanatory variable. Okay. The number of customers ahead of a person in line. Context is important. Okay, and at least in this case, they tell you to use the context. You need to know to put the context there. It is always safer to put the context there. Why risk credit if you don't? That's not a good idea. Okay, part C. One of the data points was determined to be an outlier. Circle that point on the scatter plot and explain why that point is considered an outlier. So let's go back to the scatter plot. Scatter plot is right here. An outlier, in this case, is something that doesn't follow the pattern of the data. Okay, so it says to just circle the point on the scatter plot and explain why it's an outlier. So I circled it. So that's something that I need to do. And then for part C, I might explain that this point differs from the pattern, differs significantly or strongly from the pattern of the rest of the data. This was an unusually low checkout time. For this many customers in line. Okay. It is not enough just to say that the point has a large residual, because if you had a model where the data were more scattered around the line, all the points could have large residuals. It has a large residual relative to the other points in the data set. That's something that you could say. It has to be relative to the other residuals. If you look at the residuals for all the other points, they are generally much smaller than this particular residual for this particular point. Okay, so again, context is important. Okay, you definitely this is a case where when you look at the scoring, you didn't necessarily need to have context to get the to get the essentially correct on this part, but context is always a plus. Okay? So if your response was between a 3 and a 4, or between 2 and a 3, the strength of your communication will generally bump you up to the next level if you're doing very well with the communication part. Okay, so that's question 1. Here's question 2. An environmental science teacher at a high school with a large population of students wanted to estimate the proportion of students at the school who regularly recycle plastic bottles. Okay, and so you can read the rest of it. The important part here is the teacher selected a random sample of the students at the school to survey. Each selected student went into the teacher's office one at a time and was asked to respond yes or no to this question. All right, so lots of fun stuff going on here. You're given a confidence interval, a confidence level, and you're asked how many students were in the sample selected by the environmental science teacher. Wow, we're just pulling out the big guns here on question 2. Okay, this is really this is a fairly when you know what the components of this question are, it's a relatively straightforward question, but you do need to spend a little bit of time with one of these guys. In this case, you need a calculator to really kind of get the sense of what's going on. So let's go ahead and let's look at this question. The number of students in the sample, we need something that relates to the number of students in the sample. All we have is an interval. Okay, we know in general that the interval is made larger by fewer students, but we just have nothing to compare it to. So when we're going to answer a question like this, let's think back about all the things that we know. We know that this confidence interval, let's rewrite this confidence interval in a different form. Okay, so what I'm going to do is I'm going to find the midpoint of the confidence interval. I'm going to do that by adding the endpoints together and dividing by 2. And I see, oh, wait a second. Okay, this interval is 0.7 plus or minus 0.116. Okay, and this decomposition tells me, first off, this is the point estimate. This is the p hat observed in the study. And this is our margin of error. Now, the margin of error is very important because the margin of error is equal to the standard score. Okay, and so p hat, I'm going to write the work because, hey, I love communication, right? And then the margin of error is very important. So for part A, this is really what we're after. The margin of error equals 0.116. Because this is a 1 proportion z interval, this is a critical z score times the standard error for the statistic. Okay. Since this is a z interval for a population proportion. Population, let me write that out. Okay, because this is a z interval for a population proportion, and I know p hat, and I know z star. I actually know z star. Okay, if you don't have z star memorized, you should know that common z stars for one prop z ints. So a z star for 95% CI. Let me actually write down some of the confidence level. Okay. All right, and these can be found using inverse norm if you're not real sure about it. So the z star for a 95% confidence level is 1.96. Okay. For a 99% confidence level, it is 2.576. And for a 90% confidence level, it's 1.645. Verify that on the calculator real quick. Good. Right. So I know that in this case, Z star is 1.96, P hat is 0.7, 1 minus P hat is 0.3, and I'm left with an unknown N. Now I need to do a little bit of algebra. Okay. So 0.116 over 1.96. I'm going to skip steps here a little bit in the interest of time. And so the number of students in the sample must be 0.7 times 0.3 times the square of the reciprocal of this fraction. So multiply both sides by n and divide both sides by the left-hand side. Okay, and so 0.7 times 0.3 times 1.96 over 0.116 squared. That number is 59.95. You can just round to the nearest person in this case because this isn't a margin of error. So there must have been 60 students in the sample. That's for part A. Okay. That, again, big guns there. Okay. The rest of the problem isn't quite so traumatic. Given the method used by this environmental science teacher to collect the responses, explain how bias might have been introduced. Bias is not just a catch-all term for something that's wrong with the design. If you're going to invoke a bias on the AP Stat exam, you need to be able to say both where the bias comes from as well as the direction of the bias. Okay, and so in this case, this looks like a classic case of response bias because students are being marched into the environmental science teacher's office one at a time being asked to respond to this question. And so we might if you just write response bias, that's not enough. I need to actually say what's going on here. This does to me look like a case of response bias. Students were asked face to face by an environmental science teacher whether or not they recycle. Okay. We would expect students to respond yes more often, even if it is true that they do not recycle. This means that P hat 0.7 is likely an overestimate of the percentage of people who would respond yes to the question. And that I want to talk about that for just a second. Okay, I want to talk about that for just a second, because what's being measured here is the proportion of people who would respond in a certain way to the question. We're hoping that the people who would respond to the question in that way, that actually reflects what their beliefs are and what their actual practice is, assuming that you think recycling is a good thing. And in this case, we would expect that face-to-face with that level, the behavior or the stature of the interviewer and the student-teacher relationship, environmental science teacher, we would expect that more students would say yes, they do recycle, even if they really would normally say no. Okay, and so that's an important distinction. Here's a perfect case of just using the stem of the question to answer. You should. I don't believe that when it was necessarily scored that you really had to make that distinction, but what you really do need to know is that basically the way that that you describe any kind of context should be based. Use the words in the stem to help you, basically. All right. So the statistics teacher was concerned about this bias. To obtain a less biased estimate, the stat teacher used an alternate method. And so in private, they flipped a coin, and if they respond, if they said heads, if they got heads on the coin, they must respond no, regardless of whether they recycled or not. So, but this is actually a very common method of collecting data about sensitive issues. Basically, this is a plausible out for you to sort of remove some of the stigma of telling an answer that might be untruthful. Like, for example, you might use this to say, like, do you use, like, if you're asking somebody about whether they, or sampling people about whether they use drugs, you might use this method, flip a coin. If it comes up heads, you must respond yes. Regardless of whether or not you actually use drugs. And that way, if you said yes, you don't, if somebody asks you if you said yes, you don't have, you can just say, yeah, I mean, the coin came up heads, so I had to say yes. Yeah. And so basically, in part A, what is the expected number of students from the sample who would be required to respond no because the coin flip resulted in heads? Well, it's a fair coin, so the probability of heads is 1/2. And so 1/2 of 300 is 150. Okay. Then the results of the sample showed that 213 of the selected students responded no. Based on the results, give a point estimate of the proportion of all students who would respond yes to the question. So this 213 out of 300 we expect 150 are due to the coin. Okay, so that we're going to remove 150 from both the numerator and the denominator. Okay, and so when we do that, we're going to say we're going to subtract 150 from so that gives 63 out of 150 no's expected from truthful answers. Does that make sense? Hopefully it does. And so then our p hat would now, for yeses, would be 87 out of 150. Okay, and so 87 out of 150 is 0.58. And that's question 2. Okay. Moving right along. Question 3. Approximately 3.5% of all children born in a certain region are from multiple births. Of the children born in the region from multiple births, 22% are left-handed. Okay. Of the children born in the region who are from single births, 11% are left-handed. Huh. This looks a lot like a tree diagram. You're just given an organization, right? Okay, and so this is single births and multiple births. This just screams tree diagram. And let's see what let's see if we agree that that's kind of what's happening here. And then we have left-handed and right-handed. Often when you have two categories like this, a tree diagram or table is a good way of organizing it. We're going to start with the tree diagram because I have a suspicion about what's going to happen with this problem. Of the children born in the region who are from multiple births, 22% are left-handed, meaning 78% are right-handed. From single births, 11% are left-handed, meaning 89% are right-handed, okay, because those are mutually exclusive in theory. All right, so for part A, what is the probability that a randomly selected child born in the region is left-handed? Okay, so let's go ahead and let's take a look at that. Okay, so from organizing this, this is an important way of going. So basically, the tree diagram is enough of a strategy. Okay, so the probability of left-handed is equal to the probability that a single birth child will be left-handed plus the probability that a multiple birth child will be left-handed. That is 11.4%. You can round if you want to. Okay, so for part B, what is the probability that a randomly selected child is a child from a multiple birth, given that the child selected is left-handed? So the probability of multiple birth given that the child is left-handed. Okay. Now, the way that the formula sheet was in previous years, you had to kind of piece this together a little bit. What's kind of cool is that they give you a formula on the formula sheet now that you can read directly. Okay, so the probability of multiple births given left-handedness is the joint probability that you're both multiple birth and left-handed divided by left-handed. And basically, what percent of the time that someone is left-handed does it come from a multiple birth? Okay, so the probability of being both multiple birth and left-handed is just following that part of the tree diagram. Okay, so that's 0.035 times 0.22 divided by 0.78. No, sorry. Right, and so the probability that you're left-handed was, I saw a number, I wrote it down. That's not what I meant to do. Okay, so 0.035 times 0.22 times divided by the probability that you got in part A, which is why it was part A, because you need it now. This is 0.0676. That's part B. Okay, so part C, a random sample of 20 children born in the region will be selected. What is the probability that the sample will have at least 3 children who are left-handed? A random sample of 20 children born in the region. And so because it's all children are up for grabs here, the probability that any single one of them will be left-handed comes from part A again, okay? So part C says, basically, the number of left-handed children in a random sample of 20 is a binomial random variable. And how do we know it's binomial? We know it's binomial because our textbook uses a thing called bins. So it's a binary. They either are left-handed or not. The trials are independent because 20 is less than 10% of probably all the children in this region because you're sampling without replacement. Okay, you have a fixed number of trials and you are counting the number of successes, BINS. Okay, and so it's a binomial random variable with n equals 20 and p equals 0.11385. Okay, now there's a formula for this, and it says at least 3. Okay, the probability of at least 3, okay, at least 3 is basically 1 minus the probability of being less than 2. Okay, and the reason I say that is that most of the time, what you're probably going to do is reach for a calculator. If you're reaching for a calculator, then you do need to use a basically correct. You need a calculator. If you're going to use a calculator statement for this and not use the formula, and the formula is very complicated here because it's actually the sum of 0, 1, and 2. And so you would need to subtract out all 3 of those probabilities, and that's a lot of writing, folks. And so you could get away, if you were careful, you could do the following. This is calculator speak. It's not AP calculator. So basically, you need to most things will do this for. That's why I've been trying as much as possible to correctly identify binomial with N and P. So the good folks at the AP who are reading my response know that I know what I'm doing. Okay, and so if you have 20 trials with a success probability 0.11385 and probability of 2, so then the correct statement would be 20.11385 2. Okay, and so this is my desired value of x, and this is my n, and this is my p, and so that's 1 minus. Let me see if I remembered to put the 1 minus in already. Okay, let me do that again. That is 0.0404. Okay. I seem to have blown something here. Let's try that because that number looks really wrong. Okay. So let's check our work. There are 20 trials. The success probability is 0.11385. Yep. Let's see. 20 trials, 2 successes. CDF is going to add up all of them. There, yeah, I put it in wrong. That's why I was just like, that number is super strange. So sorry about that. It's good to have number sense. Like I was just looking at the number I got negative 0.4. I was like, that's not right. Okay, 0.40221. Good. Okay, so the calculator can hurt you sometimes if you are putting in weird numbers and you don't know exactly what happened. I think I had an extra command on there somewhere. The command's hard to read. So just have a sense that of whether numbers are reasonable. You don't expect there to be a lot of successes, which is why this is a fairly good estimate, 0.5979. Because we would expect the mean to be around 2. So the fact that I got a number that was so low is very disturbing. Okay, we're moving on. Here's question 4. All right, the ACL is one of the ligaments that helps stabilize the knee. Surgery is often recommended if the ACL is completely torn, and recovery time from the surgery can be lengthy. So they designed a new surgical procedure designed to reduce the average recovery time. To test the effectiveness, a study was conducted, which 210 patients needing surgery were randomly assigned, magic words, randomly assigned to receive either the standard procedure or the new procedure. So for part A, based on the design of the study, would a statistically significant result, meaning that that what we observe in the study is an effect that would be very improbable if the null hypothesis were true, would that result allow the medical center to conclude that the new procedure causes a recovery time? And here's the word, causes a reduction in recovery time. Okay, that word is magical, causes here in experimental design. They may not call it out explicitly, but it is something that you need to be familiar with. Okay, so for part A, yes. The reason that the answer is for part A, since treatments were randomly assigned, since subjects were randomly assigned to treatments, I think that's the better way. Since subjects were randomly assigned to treatments, the groups are likely only to differ systematically by which treatment they received. Okay. This means that a significant difference is likely due only to that treatment. It's a classic cause and effect answer. Okay. And then part B. Summary statistics on the recovery times are shown in the table. Okay, I see something very interesting. I see, how many samples do I see? I see 2 samples, and I see 2 means. This appears to me that what we're looking at the question, do the data provide convincing statistical evidence that those who receive the new procedure will have less recovery time from the surgery on average? Less recovery time. Okay. Unless you are wise to the ways of constructing one-sided confidence intervals, the question here is not asking you to estimate the amount of the reduction. It's simply, do you have evidence that there is a reduction on average for the new for recovery time in the new procedure? This screams a one-sided 2-sample t-test. Okay. If you've seen me work one of these before, you know that the template I use for writing what's in a hypothesis test is called phantoms. Okay, so when I write phantoms, I'm going to ask myself, did I do all the following things? I need to define some parameters. Okay, so the parameters, there's a standard and a new treatment. So we're going to let mu s be the true mean recovery time under the standard procedure. And then we're going to let mu n be the true mean recovery time under the new procedure. Those are my parameters. My hypotheses need to be stated in terms of these parameters. My null hypothesis is that there will be no difference between the two. I want to know whether the new procedure provides a reduction in that time. In other words, I want to have an idea of whether I can tell if the standard procedure has a greater recovery time. So that's why that's written here in this way. I like to write them this way because it reminds you of what you're doing. You could alternatively write them, no pun intended, as the mean times are the same. The alternative is that the standard procedure has a longer recovery time than the new procedure. Okay, so either of these ways of writing those hypotheses are good. Okay, so those are my hypotheses. Okay, my assumptions, and I like to do both of these at the same time. Okay, so let's do them first. All right, I'm looking to conduct a 2-sample t-test for a difference in 2 population means. The two is probably redundant there, or a difference between. Okay. That's the name of the test. Okay, because I've named the test, I don't need to actually write any of the formulas in relation to it. You're going to notice that I don't choose in general to copy the formulas down, because I feel like that's pretty error prone. And that's time that you don't need to spend if you understand the name of the procedure that you're running. Okay, so a two-sample t-test for a difference in two population means. I need to check conditions to see whether this is an appropriate test to run. Okay, and so basically a two-sample t-test means that I need to be convinced that the underlying sample distributions of both samples would be approximately normal with the proper spread. Okay, so that means I basically need to check the conditions twice for each one. You're going to see that this is going to work pretty well. The normality condition is the shape condition. I'm actually going to write that on here. Okay, so the shape condition, and the number of people in the standard treatment group, 110. It's bigger than or equal to 30. Okay, and it's a difference in means. So that's why I'm checking that it's at least 30. And the people in the new group, that is 100, which is bigger than 30. So this condition is met. Okay. Now I need to check whether there is a random condition. The subjects were randomly assigned to treatments. Independent. Spread. Normally, this is where you check the 10% condition, but I want to emphasize that because the subjects were randomly assigned to treatments, it takes care of the independence. We don't want to check the you don't need to check the 10% condition here. Okay, so that's my A and my N. Okay. Now we actually need a test statistic. Okay, to run the test, I'm going to use a two sample t-test. Okay, there are in case you're wondering, like if you're looking at a typical TI-84, the z-test and t-test are one sample tests. They don't say one samp. I know that the proportion things all say one prop, and I wish these said one samp, but they don't. And same thing with t-interval. Okay. By the way, if you're using a z-test on the AP exam, you'd better know what you're doing. You almost never use the z-test on the AP exam because the z-test option 1 is only used when you know the population standard deviation for the one sample that you're taking. Okay. This is a two sample t-test, which is option 4 on my computer, like your calculator. It's a computer, basically. Your mileage may vary. You probably get a menu like this, and the stats from the table are definitely what you should input in here. Okay, so you actually need to conduct this from start to finish. I'm going to use the first population as, and be careful that you put the data in the right order. The mean comes first, then the standard deviation. I'm going to let the first group be the standard group. And I'm going to let the second group be the new group, because that's the way I've written the hypotheses. And because the way I've written the hypotheses, I want to show that the mean for the first group is larger. In this case, we are not going to make the pooled assumption. In general, you should never make the pooled assumption on the AP exam, because we don't believe that these two populations should have the same variance. So you don't pool them. If you happen to know that they do, then you can, but there's no, you shouldn't. Okay, so now you need to write down a few things in order to execute the test properly. By technology, the t-value for the test, I got 7.127. Okay, with the number of degrees of freedom. The calculator always uses the fancy number of degrees of freedom. I'd like to put little slashes in my 7s, just so I know that they're 7s and not 2s, because my 2s are terrible. the calculator uses the more powerful way of calculating degrees of freedom. When you combine the two t-tests, you don't have to just use this n-1 for the smaller sample. You can actually have many more degrees of freedom than that. So this is a very this is a more powerful test. Okay, and the p-value. And so obtain p-value is the O of phantoms. It's 8.358 times 10 to the negative 12. If you get a p-value of 8.358, that's a probability. It shouldn't be 8.358, right? You need to make sure that you include the e to the minus the e minus 12. Please don't write e minus 12. It's scientific notation. It's times 10 to the minus 12. Okay, so that's my t and my O. Okay, I'm going to make a decision. Okay. Letting alpha equal 0.05, the p-value, I'm just going to write it again, 8.358 times 10 to the negative 12 is less than alpha. Therefore, we reject the null hypothesis. Okay. We have sufficient evidence. This is the S. Sufficient evidence. State a conclusion in context. The new procedure has a lower mean recovery time. That is question 4. So again, phantoms, parameter, hypothesis, assumptions, name of test, test statistic values, including degrees of freedom for a t-test. O, obtain p-value. M, make a decision. Clearly state your context, and S and your mechanism for making a decision in M. Okay. Your teacher might have taught you other ways to do this, like you might have a rejection region approach. I'm not going to cover that here, but if you do have a question, then pop it in the chat or pop it in that ask a question button. Okay. And I'm not seeing questions asked, which is why I'm just plowing through these. I don't see anything in the chat. So yeah, let me know if there's something that you want to go over. All right, question 5. The following histogram summarize the teaching year for the teachers at 2 high schools. Teaching year recorded as an integer. First year teachers recorded as 1, and so on and so forth. All right, so there's a there's a histogram here. It's kind of weird to see this question show up as question 5, but it does ask, if you look at part A, the median teaching year for one high school is 6, and the median teaching year for the other high school is 7. That is important, super important, very important. Okay, and so what we need to do is actually figure out, do we have the information here? The means are the same. You're told that the means are the same. Okay. But do we have enough information to figure out what's going on? We know that there are 221 teachers at high school B. Okay. And so I'm actually going to engage in a little bit of graph reading. And I'm going to use this fact, 221 teachers at high school B. I'm going to use that fact to help me out here, because I see that the frequency in high school B, I'm going to just start reading some bars. Okay, so I see that this frequency might be 78, it might be 79. I'll just put it 79 question mark, and this frequency looks like it's about 34. Right? Okay. Now you should know from a histogram that the left endpoint's included, but the right endpoint's generally not. And so what I see here is that the combined frequency of these two classes here is somewhere in the neighborhood of 112 to 114. Okay, so for part A, I'm going to say the following. Histogram B has a combined frequency of basically 79 and 34 of somewhere in the neighborhood of 111 to 113. Okay, I'm guessing it's somewhere in that neighborhood already. We know the median combined frequency. I forgot to say in its first two bins, and that is 1 less than or equal to teaching year less than 7. Less than 7 is very important, okay? We know that the basically, if you think about taking 221 and splitting it into halves, you end up with 110, 110, and 1 left over. So the 111th observation in histogram B is the median. So school B must have a median of 6. This means school A has a median of 7. Okay, and say the median, I should probably add the context because high school B, another way to say this is, another way to look at this is that high school B's mean must be strongly influenced by its strong right skew, right? And so the right skew would have a more pronounced effect on school B than school A. And because the means are both 8.2, that profound effect must mean that high school B has the lower median. Okay, but you do need to cite a specific piece of evidence that you got from the graphs. Okay, you can't just say like, oh, it looks like high school B has a bunch of people on the left. Okay, so you need a good justification there. Okay, part B. An additional 18 teachers were not included with the data recorded from the 200 teachers at high school A. The mean teaching year of those 18 teachers is 2.5. Okay, so the mean of 200. So 200 from A have a mean of 8.2. Okay, so their sum of the teaching years is 8.2 times 200, right? And then there are additional 18 from A with mean 2.5. And so the sum of those teaching years is 18, or 2.5 times 18. Okay. And so the reason I'm telling you this is that if I want to know the mean of a data set, I add everything up and then divide by how many there are. I don't have necessarily the exact data, nor do I want to try to reconstruct it from that histogram, but I can use the fact that I know the mean to know what the sum must be. So for example, 8.2 times 200 is 1640. And that 2.5 times 18 is 45. So the mean of all 218 must be the sum of the sums divided by how many there are, knowing now how many there are. And you would expect it to bring the mean down, but with only 18 teachers, it's a question of whether that effect is going to be super great. Bring it down a little, it brings about half a year. Okay. That's part B. Part C. The standard deviation of the teaching years for the 221 teachers at high school B is 7.2. If one teacher is selected at random from high school B, what is the probability that the teaching year for the selected teacher will be within one standard deviation of the mean of 8.2? Okay, so that is within one standard deviation. Means the year is in the interval 8.2 plus or minus 7.2. Here, I'm going to basically say 1, the year is between 1 and 15.4. And within, I'm going to include the 1, I'm going to include the endpoints. Okay. Teaching year recorded as an integer, so that means that you're only going to count the numbers from 1 to 15. Okay. Right, so I'm going to have to do a little bit more counting. Okay. So the good news is that 16 is not included in the 5th bar. So I know that everything to the left of this is between 1 and 15. So I better just keep counting. Okay, so 79, 34. Any reasonable estimate will do, to be honest, because like you can tell that's probably 34. Honestly, this is probably 28. It's a little, if that's 28, the one next to it is going to be 29. I think it is possible to make that judgment. And then this is 19. Okay, so the percentage of teachers in the interval is 79 plus 34 plus 28 plus 29 plus 19 over the total number that there are, which is 221. Okay, and that number is approximately, that's 189 in the numerator divided by 221. That's about 85.5%. I said percent, so I'm going to stick to my guns here. But I do need to make sure I write percent, or I'm going to be very sad. If you wanted to, you could use more probability notation here as well, but it is not necessary. Okay. So that's question 5. Okay, like I said, we're likely to run over here because question 6 is a good one. This is a really good one. This is one of the rare cases where you might have actually done this calculation in class. It's very rare for that to happen in question 6. We know that there isn't going to be a question 6 style question this year. All right, systolic blood pressure is the amount of pressure, so on and so forth. The mean systolic blood pressure is reported to be 122 millimeters of mercury with standard deviation 15. Okay. All right, and so we're going to select a random sample of employees within this very large corporation. Okay, and then we're going to calculate the sample mean. So this is a one mean t-test. This is a t-test for a population mean. And you see that it's one-sided. Describing a type 2 error, then, in the context of the hypothesis test, there's a lot to write, so I'm going to go ahead and just write it up here. A type 2 error is when you, it's basically it's false negative. You fail to reject the null hypothesis when you should have. A type 2 error means concluding the mean systolic blood pressure was not larger than 122 millimeters mercury when, in fact, it was larger than 122 millimeters mercury. It's not enough just to write we failed to reject the null hypothesis when we should have and leave it at that. Here's the context. So we would means concluding the mean systolic amount was not larger. Failing, in other words, this is failing to reject the null hypothesis. And type 1 error would be rejecting the null hypothesis when the null hypothesis really was true. So for me, the type 1 error is that the first thing was really true and you did the wrong thing. And the type 2 error means the second hypothesis was true and you did the wrong thing. Okay, part B. Assume that sigma, the standard deviation of the systolic blood pressure of all employees, is 15. if mu equals 122, the sampling distribution of x bar for size, well, and so on and so forth, what values of the sample mean x bar would represent sufficient evidence to reject the null hypothesis at the significance level of alpha equals 0.05? Okay, so for part B, we're going to draw the hypothesized sampling distribution. And so our hypothesized sampling distribution of x bar is going to be approximately normal with a mean of 122 and a standard deviation of 15. Oh, well, it tells us 1.5. I was going to say the reason where we got this number is 1.5 is equal to 15 over the square root of the sample size, but we don't need to worry about that. Okay, when we draw we want to include 3 standard deviations out either way. Okay, so we definitely want to include enough context to show that we know what it is that we're doing. Now, what would have caused the null hypothesis to have been, what values of the sampling x bar would represent sufficient evidence to reject the null hypothesis at the significance level alpha equals 0.05? Because this is a one-sided test. It's a one-sided test with the greater than, right? This is a one-sided test. That means that, or we often call them one-tailed tests. And the reason that it's a one-tailed test is that the area of this test, or the area of the rejection region, this is actually a rejection region problem. Okay? So the rejection region would be any sample mean in this shaded area, which has an area of 0.05, which equals alpha. Okay, so that's super important to keep in mind, because now I want to know what this value is. I want to know what the boundary of the rejection region is. Okay, so any x bar above this value causes the null hypothesis to be rejected. Okay. The lowest x bar that causing rejection of the null hypothesis is going to be equal to, and here I think it's important here. Let's use in norm, okay? And so this is a left, if the area on the right is 0.05, the area on the left is 0.95. And your calculator has the option of using mean and sigma. I don't need to calculate the z-score for 0.95. It's going to be 1.645. Okay, but what you can do is the left area. Okay, so I'm labeling my calculator commands so that the readers know that I know what I'm doing, and the diagram helps them understand that I know what I'm doing. So that this is probably the bare minimum amount of communication I need to make so that a reader knows that I know what I'm doing. Okay, so any x bar bigger than or well, not equal, because it's we tend to use a less than strict. So any x bar bigger than 124.567 will cause rejection of the null hypothesis. That's part B. All right, part C. Using the, all right, this is, I love this question. Okay, so for part C, using the actual mean of 125 millimeters mercury and the results from part B, determine the probability that the null hypothesis will be rejected. And notice that they haven't given you a lot to go on here, but you can still do this yourself. Okay. What I'm actually going to do is I'm going to draw the distribution for part C. I'm going to make sure that the 125 mean aligns. Okay. And now, it's a terrible normal curve. Okay, that's good enough. How y'all doing? All right. Here now, I'm going to extend this. And what I'm aiming to do is make sure that these two curves can be compared visually. And so I've gone 3 standard deviations in either direction. And so in this case, the X bars really don't come from the hypothesized distribution in B. The X bars really come from the distribution in C, because that's actually the true mean. Okay, so X bar really does follow a normal distribution with a mean of 125 instead. And now we need to know where that fit. Now we need to know where that 1.5 came from, right? If you wrote 15, looking at the number in the stem of the problem, and then didn't recognize that this is a population standard deviation, not the spread of the sampling distribution, you are in trouble. You're not getting this question right. Okay. So that's why this also has a distribution of the standard deviation, this distribution of 1.5. That's why these two things are aligned so carefully, right? But now I want to know, that is a poor representation. I'm looking up here because that's just where I threw it, just because I wasn't really sure. I really should have. Let me actually go ahead and put it where we know it is now. So 1 standard. So 5%. Okay. There we go. That's better. All right. 124.467 is below the true mean. And so you're more likely than not to reject the null hypothesis. Okay, so what I want to do is show you a number here. So this is here to the right of this is alpha. Okay. So if we're talking about making a type 2 error, then what we're doing is that means we fail to reject the null hypothesis when the null hypothesis is false. Here we know, we are told the null hypothesis is false. So this is the probability that you see here in the shaded area that we're going to get the question right. This is this area to the left then here is beta, the probability of a type 2 error. And you can see that relationship between alpha and beta. It involves these two different curves, which is why I like drawing it this way. Okay, so we're told the null hypothesis is false. Okay. So now I want to know what the actual probability that the null hypothesis will be rejected is. Okay, so the probability of rejecting not is equal to the probability that X bar is bigger than 124.467. And this is normal CDF. 124.467 to infinity, where the mean is 125 and the standard deviation is 1.5. Okay, we need to label this command. Okay, and so this is the left, the right bounds. Okay. I like to use 1E99. You don't need to use a number that big for the upper. I just like to use 1E99. Okay, and so that is 125, 1.5 paste. That is about a 64% chance. Okay, this is the probability that the null hypothesis will be rejected. Okay. This probability is equal to 1 minus beta. So this is the power. of the test, since 0.6388 equals 1 minus beta. If you have never computed power before, this is how power is computed. You can actually, but in order to compute power, you need to know the true mean. Okay? That's one of the reasons why we often say, the power of the test against a true mean of. Then because we're kind of throwing spaghetti against the wall, right? Do we actually know? Would we ever really get to know that the true mean's 125 millimeters mercury? I'm not sure. We're not divinely omnipotent, right? So it's hard to know. So we often test power against certain alternatives, and we want to know what the probability is if the mean was a certain number that we would actually reject it. And this is often used in setting policy, right? Where like we set a level such that and we specify that the power of the test, the sensitivity of the test, has to be able to detect a certain difference. Okay. And finally, the last part of the question. Part E, suppose the size of the sample to be selected is greater than 100. Would the probability of rejecting the null hypothesis be greater than, less than, or equal to the probability calculated in part C? Okay, lots of ways you could answer that. Here's one way. Okay. Raising the sample size increases the power. So the probability will be greater than that in part C. Okay. That's honestly all you need to say. Okay. As far as that, well, let's actually dig into that a little bit. That's probably all. That might be all that you've been equipped to say. To get the E and looking at the criteria, the important thing here too is that let's see if we can make a better explanation than this. Both distributions the hypothesized one for X bar and the true sampling distribution would have smaller spreads. Thus, let me show you what happens here. So this is centered at 122. So it would have a smaller spread than it used to. It's basically that case. Thus, the probability well, let's not say that. I think it's easier to say this. The X bar that would cause rejection of H naught would be lower, meaning the probability of generating an X bar that in the sample that causes rejection of H naught would increase. This is the better explanation. So this area moves up over here, and then this becomes a lot larger. So we set, this is our critical X bar for rejection. And so this area goes up. Alpha is still over here. Beta is still over here. And what we've done is we've increased the power. There we have it. All right. So thanks for sticking around for that wild ride there. Remember, what makes a good response is that you understand context, that you understand the difference between the model and reality, and that you avoid unintentional lies. Don't try to take the easy way out when writing a response. Always include the context. Always make sure that you are following the recipes for explaining common things like confidence levels, p-values, R-squared, things like that. That will make sure that you then you make the most of that. It will make sure that you make the most of the chance to get credit for all the hard work that you're putting in this class. So thank you for coming again.